transient thermal response of the underground power cables. This example is described in the IAC standard. The three-phase cables are laid in a plate formation underground. Initially, the cables are energized, but there is no electric current in the cables. The load is not connected. After some time, when the temperature is stabilized, the load is connected, the current starts to flow, and the task is to calculate the temperature rise dynamics. In my previous videos, I already demonstrated how to calculate dielectric losses in the cable and how to calculate the temperature caused by these losses. Also, I simulated AC magnetic problem and calculated the currents and losses in the sheaves in the cross-bonding cable. Now I need to simulate transient thermal problem and calculate the temperature rise dynamics. Let me outline the simulation workflow. Transient thermal problem takes three input parameters: dielectric losses, initial temperature distribution, and the magnetic losses. To be able to pass this data automatically in transient problem, I need to make sure that all simulation problems are based on the same geometry model file. Then I will be able to run the transient thermal problem. Okay, let's start QuickField now. In my previous videos, I have already demonstrated how to set up and simulate AC conduction problem and AC magnetic problem. Here is just a brief review. AC conduction problem is used to calculate electric field stress distribution in the insulation. I specify the frequency, I specify for the insulation the dielectric permittivity and effective electrical conductivity that takes into account dielectric losses. And once the problem is solved, you can see the electric field distribution, you can adjust the field picture and get the Joule heat distribution. You see the distribution is the same in each cable, and you can click to select and calculate the integral. Active power produced in the cable per 1 kilometer of the conductor length, so this would be 12 watts per 1 meter of the cable length. And we had a steady state heat transfer problem that takes dielectric losses as an input parameter and calculates the temperature distribution. Here you can see the temperature distribution caused by the dielectric losses. In magnetic problem, we have specified currents in the conductors, and for conductors we also specified the electrical conductivity. So QuickField calculates the losses. There are in fact three sections with interconnected sheaves, and all three sections are placed in the same geometry model file. So in the results, you will see three cross sections. Each section length is 7 kilometers. And here again, I can calculate the losses, but this time the losses in the conductors. Click to select the conductor. Joule heat per 7 kilometers of the cable length. If I divide this by 7 kilometers, 31.6 watts per 1 meter of the cable length, and in the sheave, this value, (1.8 watts per 1 meter of the cable length. And here in the folder, you can see all the simulation files. We have electric problem, thermal problem, and magnetic problem. Electric and thermal problem use the same geometry model file. Here it is. And magnetic problem use this geometry model file. So my first task is to make sure that all these problems use the same geometry model file. So I'm going to change the geometry file for electric and heat transfer problems. But first of all, let's copy all these files and make new folder and paste them here. In QuickField, I open electric problem, follow to the problem properties, change the cable length to 7 kilometers because this cable length is used in magnetic problem. And I change the reference to the geometry model file. Here it is. Okay. Let's take a look what we have in the data file and what we have in the geometry model. This is essentially the same three-phase cable here, but in previous geometry model we had only one cross section. Now we had 3 cross sections. Some labels are the same in the new and the old geometry model, for example, the air. But some labels are different. Here, this block is called earth, and in previous geometry model, it was called soil. In this list, QuickField displays not only the label that present in the data file, but also the labels that are assigned in the geometry model, and the labels that were assigned to the geometric objects and do not have the counterpart in the data file have the question mark next to the label name. We have a simple technical task. We need to match labels in the data file to the labels in the geometric model. Click here. This block has label earth. Previously, it was called soil, so I renamed the label in the data file. Match. Previously, the conductor has label A. Now it is called conductor A. Well, I renamed this label conductor A. Match. You see no more question mark here. This is conductor B. And this is conductor C. Now, next label with the question mark. Conductor screen. Here it is. I just need to rename this. Conductor screen. Okay. And the core screen. Here it is. Core screen. Now, what are the labels with question mark we have here? Shift A, B, C. In previous geometry model, they were called A shift, B shift, C shift. Let's rename them. Shift A1, shift B1, and shift C1. In previous geometry model, we had only one cross section. Now we have 3 cross sections, so you can see shift A1, A2, A3. I just need to copy this label. This would be shift A2, and this would be shift A3, and the same for the shift B. Copy and paste. Shift B2, shift B3, and the same for the shift C. shift C2 and the shift C3. Now that's all. We do not have any more labels with question marks. Let's check the labels for the edges. Remember in electric problem we had labels for the edges that were assigned to the conductor surface, and we had label 0 assigned to the sheave surface. These labels are used to specify electric potential. I need to introduce them to the new geometry model as well, because now if I click the label and switch to the geometry model, I will see that nothing is selected. If I select the block, I will see selection section. But if I click the label, I will see the selection section. But if I click this label, nothing. Okay, let's zoom in. Switch to select object mode, click to select, hold the control button, press to select multiple objects at the same time, and assign label U. And these edges would have label 0. This is the sheave electric potential. And I need to repeat this for all other cables. And here in the folder you can see all. And here in the folder you can see all the simulation files. We have electric problem, thermal problem, and magnetic problem. Electric and thermal problem use the same geometry model file. Here it is. And magnetic problem use this geometry model file. So my first task is to make file for electric. So let's copy all these files and make new folder. And paste them here. Okay, we can solve the electric problem now. Let's take a look at the results and calculate the losses in the cable. Zoom in. Use the contour tool, click to select the cable, integrals, 84 kilowatts per 7 kilometer of the cable length. This would be 12.1 watts per 1 meter of the cable length. And what we had previously, this is the electric problem, and the losses were 12.1 kilowatts per 1 kilometer of the cable length, or 12.1 watts per 1 meter of the cable length. So the losses are the same. But now this problem is based on the new geometry model file that includes 3 cross sections. Okay, next problem I need to change is the cable head. Open it. Again, I open the problem properties and change the link to the geometry model file, cable AC, and change the geometry model length. It should be 7 kilometers. Okay. Again, I will open the data file and I will open the geometry model. Here it is. These are the labels stored in the data file. And these are all the labels stored in the data file and assigned to the geometry model objects. We need to match data file and the geometry model. Again, I should rename soil to F. I should rename A to conductor A, B to conductor B, and C to conductor C, and shift to shift C1, shift B1, and shift A1. And I should rename the core screen to core SCR and the conductor screen to con.acr. In previous geometry model, we had only one cross section. Now we had 3 cross sections, so I need just to copy these labels and rename them. That's all for block labels. Now for the edge labels, we already assigned U and 0 labels to the geometric model objects. This is the boundary. This is the soil surface. I need to assign this label to the soil surface. In the geometry model, click to select the soil surface, hold the control button to select multiple objects at the same time, and assign a label. Okay, now I can solve the transfer problem. And we can got an error message. The linked problem results are out of date. Electric problem results are out of date. That happens because both problems are based on the same geometry model file, and we have just modified the geometry model. We have assigned label here. So the geometry model was modified, and I need to run the analysis again and resolve electric problem. You see the geometry model file has been modified. Let's take a look at the results. Again, let's zoom in and measure the losses in the cable. They should be the same. Indeed, they are the same. So now we can solve the thermal problem and calculate the temperature distribution caused by the dielectric losses. The problem is solved. Let's take a look at the results. Here's the temperature distribution, the same in each cross section, and the temperature rise is 28.3. Let's compare these results with the older problem results. In older problem, we had the temperature 27.9. So the difference is 0.4 degrees. And I believe the difference is caused by the fact that in all the geometry model we had more space to cool down the cable. Here the geometry model is more compact. Anyway, the temperature difference is small, so I believe we can proceed. Now we had all 3 problems based on the same geometry model file. This geometry model file we do not need anymore. I deleted. Now we can create transient thermal problem. In QuickField, I create new problem. Cable transient. Next. Problem type is transient heat transfer. Cable length is section length is 7 kilometers. Model class is plane parallel, and naturally I would like to use the same geometry model file that is used in all other problems to be able to automatically pass the data from electric, magnetic, and thermal problems here in the transient analysis problem. So I click Browse and change the geometry model file name to this one. And I believe I will reuse the data file from the steady-state heat transfer problem. I can make a copy, but if I need to change the label properties, I would have to make the corrections in 2 places. Better to have a single file. Or here I browse for the data file. Next, In transient problem, we have to specify the final simulation time and the time step. I'm going to simulate 24 hours, which is in seconds 24 multiplied by the 3600, this value, with the time step of 10 minutes, which is 600 seconds. Initial temperature I do not specify here. I'm going to import the temperature distribution. Finish. The geometry model is the same, and the labels are already assigned, and the properties are already specified. So it seems there is nothing to do here. Let me check the label properties. For time domain, we should also provide the density and the specific heat of materials to be able to calculate the temperaturized dynamics. For steady-state heat transfer, we need only to know thermal conductivity, but for transient problem, we need to know these parameters as well. Here I have the file with parameters. So for the conductor screen, which is considered to be the dielectric in thermal problem, the density is 1000 and the specific heat is this value. Okay. For the dielectric, the same density 1000 and same specific heat. Where did I get this data? In fact, the temperaturized dynamics depends on the ratio of thermal conductivity to the product of specific heat and the density. So if you open the IEC standard, for example, for the insulation, you will see that here the volumetric specific heat is specified, which is the product of specific heat and the density. And the same rule applies for the conductors. For the sheet which is made of lead, I specify the density 11,400 and specific heat 127. And the product of these two values $1.45 million. Let's look up this value in the IEC standard. Lead 1.45 millions. So the density you can look up in Wikipedia on our online resources, and using this value calculate the specific heat. Okay. And the same properties I should assign to all sheet blocks. For the dielectric and semiconductor screens, I specify 1000 and 2000. For the syringe, which is a polyethylene, I specify this is the density and this is the specific heat. And for the F, the density is this value and the specific heat is 800. For the conductors, which is copper plus some oil, the density is this value, a bit lower than the density of the pure copper. And the specific heat, this value. Now that's all, and you may have noted that we have not specified the heat source here, because I'm going to import the heat source from the electric and from the magnetic programs. So it's time to add the links to the problem. So far there are no links. Open the problem properties. Pull to the links tab, and here I will import the generated heat from the electric problem, the generated heat produced in the insulation. This is the electric problem. Add the link, and I'm going to import the heat produced in the conductors. This is a magnetic problem. And I'm going to import the initial temperature distribution from the steady state heat transfer problem. Okay, now you see there are 3 links. Let's solve the problem. And we've got an error message. The linked problem results are out of date. The magnetic problem. Indeed, we have introduced new labels here in Geometry model. We have assigned 0 and we have assigned U to the conductor surface. And remember, all these problems are based on the same Geometry model file. So I need to provide some properties for these labels in the magnetic problem as well. Yes, here it is. You see these labels have the question mark next to the label name. Well, in fact, this label doesn't have any physical meaning in magnetic problems, so I do not specify any properties here. Just open the dialog and click OK. Now you see the 0 mark next to the label name. That means that this label presents in the data file but doesn't hold any data. Anyway, the data file has been modified and we need to resolve the problem again. You see the data file was modified. Okay, the magnetic problem is solved. Let's take a look at the results. Let's measure the losses in the sheave to make sure that they are the same as they were in previous problem. Selected the sheave, joule heat per 7 kilometers of the cable length. Zoom in, click to select the same value. Okay, finally we can proceed with the transient heat transfer problem. Solve the problem. It took quite a lot of time. Let's take a look at the results. Here you can see the temperature distribution in the cable after 24 hours of working at the rated current of 1580 amperes. You can change the display time and take a look at the temperature distribution, for example, 1 hour after the current was switched on. Now let's zoom in. And if I hover below in the status bar, you can see the temperature, 35 degrees. And you can get the temperaturized dynamics on the XY plot in any point. Just right click, choose the time plot. Here you can see the temperaturized dynamics in this particular point. Initially it was 28 degrees. Now it is about 57. The exact values you can see in the timetable. Time, temperature, and other field parameters. You can add more curves here to visualize on the same XY plot temperaturized dynamics in other points. Just specify points coordinates or click any point, right click and choose the time plot. Here you are. Okay, in fact the problem is not that simple because the conductor resistance depends on the temperature. And to take this into account, we may utilize several AC magnetic problems. So the workflow is the following. We have several heat transfer problems. Each heat transfer problem simulates only a short period of time, 30 minutes. Then we use the so far calculated temperature distribution to correct resistivity of conductors, simulate yet another magnetic problem. Then we simulate next transient heat transfer problem, and each heat transfer problem takes three input parameters: dielectric losses, magnetic losses, and so far calculated temperature distribution. Next, new value of magnetic losses, same value of the dielectric losses, and so far calculated temperature distribution. This approach takes time to properly set up and link all these problems, but it gives more accurate results. You can even change the current in each intermediate AC magnetic problem, and this way you can simulate variable load and calculate the temperature response to the variable load. If you search on our website for the transient thermal response of the underground cable, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the result may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.